Nearly 2 million years ago, man began to work stone into useful implements. By flaking flint-like rocks, he was able to fashion tools with sharp cutting edges. Tools ranging from simple flakes to more complex scrapers, knives, choppers, and points. His raw materials, such as flint and obsidian, were obtained by quarrying from exposed outcrops, from surface deposits, or by collecting stones from stream beds. The earliest tools were made by relatively simple techniques, as prehistoric man learned to break stone by the proper application of force. When the force was applied, a cone formed inside the stone. And early in human history, man learned to use this cone principle as he shaped stones into tools. Here, the flintworker, Don Crabtree, removes the cortex from a large river cobble to expose the unbruised material inside. He's removing large flakes by direct percussion with a moose antler billet.
At the present time, a platform and a ridge has been prepared to guide the flake. Prior to this, large primary flakes were detached from both faces of the nodule. As you notice, the large ridge guided the blade-like flake from one end to the other.
About 400,000 years ago, near Peking, China, prehistoric man made stone tools by removing large cortex flakes from cobbles by direct percussion. These replicas made by Crabtree are similar in shape and size to those illustrated by casts of original specimens from Peking.
A large cortex flake was used to replicate the Peking chopper. The hammer stone now is being used to remove a right angle edge from a large primary flake. The backing is taken off by very small, steep flakes. This is to protect the hand of the user.
In describing the characteristics of cores and flakes, flintworkers use a number of specialized terms. These include proximal end, platform, point of applied force, bulb of force, negative bulb of force, longitudinal fissures, lateral or marginal fissures, compression rings, flake scar, derailleur scar, distal end. This large flake illustrates the bulb of force. The flake platform, and a negative bulb scar from previous flake removal. Here's another flake which shows on the platform the area contacted by the flint worker's hammer. The bulbar area shows the outline of the positive cone which formed when this flake was removed from the core. This aboriginal specimen from an obsidian quarry in eastern Oregon illustrates a cone formed when prehistoric man broke a rock against an anvil stone set in the ground. When an object strikes a vitreous rock and the blow is perpendicular to the surface, a truncated cone of percussion is formed inside the rock. The size of the cone is determined by the amount of applied force and the quality and inertia of the stone receiving the impact. In tool making, the amount of applied force depends on the size and texture of the hammerstone, the velocity of the blow, and the worker's intent and proficiency. Because the cone is contained inside the rock, it can only be examined by removing flakes from around the point of impact. This frees the cone for study.
We are here just examining the cone itself. One can see the scar of the cone on the flake. These are the scars that appear on the artifacts. Each one has very definite characteristics. And it's by the examination of the cone scars that one is able to determine the technique used.
This obsidian river cobble was cratered by hundreds of overlapping cone scars as it rolled and bounced along the stream bed. The rock was reduced in size and overlapping cones formed during this battering as bits and pieces of the rock's surface fell away. The resulting cratered surface indicates that the stone is workable material for flaking. Intersecting cones similar to those created naturally by the river were also made by early man, as he used a direct percussion technique to make tools such as this grooved maul. Whole cones may be detached from glassy material by perpendicular blows on a flat surface. This principle is illustrated by steel BBs being propelled against a sheet of plate glass. Cones are driven from the base of the glass plate because the applied force exceeds the elastic limit of the glass and causes a cone-shaped fracture. Changing light patterns emphasize the elasticity of the material. Because of its elasticity, an elongated flake may flex in the midsection without breaking, but occasionally a portion of the midsection may be unintentionally removed. This dislodged fragment is unusual because it does not have the bulb of force shown by other flakes. A similar technique, but using a punch to produce whole cones, was used in ancient times to perforate stone. Perforation can be accomplished by the use of tube drilling and the cone principle. A partial hole is drilled in the stone. Then a punch is seated on the core created by the tube drill and given a sharp blow, driving a whole cone from the opposite side and accomplishing perforation.
Similar methods taken place at different areas. In North Africa and Egypt, they have found that beads have been made by the same process as were being made in Colima, a part of Mexico. A full cone has been removed from the underside of the tabular piece of material. The material is shaped to a circular form after the perforation is made.
If a punch is seated above a right angle edge, it is possible to make a side-struck flake. This involves creating a half cone to produce a rapidly expanding flake whose width is greater than its length. Striking a blow on a punch is called indirect percussion. When the punch is seated perpendicular near a right angle edge and a sufficient amount of force applied, a rapidly expanding flake is detached. This flake has its apex at the point of impact and is bipointed at its termination on the opposite edge. A side-struck flake is preferred to other curved flakes for making pointed tools because it is strengthened by its long, straight ridge and requires a minimum of retouch. Cones can be struck from alternate faces. In this case, some part of each half-cone scar serves as the platform for removing the next flake from the opposite face. This piece is broken because of a flaw in the material. The flintworker's thigh is yielding and reduces shock to the stone during removal of the 90-degree edge of a tabular piece of siltstone. This kind of flaking leaves the edge on the median line of the core. Flakes removed from alternate faces leave projections which can be used as striking platforms for further thinning. Alternate flake scars produce a sinuous edge with multiple platforms. The funnel shows the angle at which force was applied to remove a flake or cone part. This archaeological specimen shows a sheared cone and the flat face which results.
There's a half of a truncated cone at the top of the split cobble. We'll notice the arrailure scars, the radiating fracture lines, the ripple marks. These are good for identification of the direction of force.
A block of stone may be broken by resting it on an anvil of adequate size and weight and striking it with sufficient force and accuracy. A cone forms and is sheared along a face where it is unsupported by the anvil. The effect may be replicated by direct percussion on a core supported by an anvil so that the shear takes place on a plane between two opposing forces.
The technique of splitting a cobble is most useful because it affords one two pieces which can be used efficiently.
The flintworker uses the cone principle to detach a flake of predetermined size, shape, and thickness from a specified part of the core face. This control permitted prehistoric man to select with accuracy where a fracture would occur. If the design of the tool demands, the flintworker can intentionally distort the cone. Part of the face of the cone is lined up with the face of the core so that it becomes the dorsal side of the flake.
A suitable striking area must be prepared on the margin to conduct the force in the right direction into the block of material being used. The fingers on the underside feel the position of the material, and by using and taking advantage of ridges and protuberances, one can anticipate where the fracture will take place. Each flake requires a different amount of force, a different intensity of blow, depending on the amount of area that is to be fractured. By striking too hard, the flake will shatter.
Whether intentional or unintentional, flintworkers of the past were taking advantage of the cone principle. Use of the fracture angle of the cone is manifest on the Paleolithic cleaver found in archaeological sites in Europe. The cutting edge required skillful control of the cone in order to make and move tabular flakes. The work starts with percussion preforming of either a core or a large flake of flint-like material.
A flake will be taken from the distal end of this particular artifact. We'll make a knife edge, and it'll have a very sharp cutting edge rather than being a pointed tip. The angles that must be conceived are very critical because a flake must be removed across the face of the artifact.
Two angles must be calculated to get the proper bevel on a cutting edge at right angles to the long axis of the object. The direction of the tranchant blow must be tangent to the cutting edge desired. And the angle of the cone must permit the flake to carry across the entire face of the object. Once mastered, this technique permitted the consistent production of heavy, sharp-edged tools.
The flake is removed from the distal end. It's a very distinctive flake, and it has certain qualities that are identifiable. This object, rather than being pointed, has a transverse cutting edge and is more axe-like than the regular hand axe.
Like the prehistoric cleaver, the modern replica has a sharp, straight cutting edge and could be used for diverse cutting needs. The cleaver has an added advantage. When its edge is dulled by use, it can be resharpened by detaching another flake by the tranchant blow. The making of a tool by direct percussion illustrates the way in which a prehistoric flintworker made one of the most common tools in human history, the hand axe. It was probably used for killing game, skinning and butchering animals, cutting wood, digging, and for hammering. The technique appears simple because it's the work of a master craftsman.
Individual platforms are not prepared during this technique, but the flake scars from the opposite edge provide the platforms in order to remove the margins. It's flaked on all sides except the end that is held in the hand. The flakes that are flying are very dangerous, and the worker must guard himself against getting severe cuts in making this object. The tool may be made as thick or as thin or at whatever weight the worker desires. Be made very rapidly. They may be reshaped easily. Edge. These objects are found in many places in the world.
The principles of stoneworking are reflected in the cone of percussion. The direction of force, the use of pressure, fracturing by exceeding the elastic limits of the material, whole cones, making beads, reduction of prediction of flake fracture, percussion flaking, the cutting edge of prehistoric tools, a core replica, and